Okay, so let's start my talk. So firstly, thank you for the organizer to invite me to this very good, nice place and the good opportunity to give the presentation of the cosmic ray energy spectrum measurement by Pierre Auger Observatory and the telescope array. So today I would like to talk about the spectral measurement, not only the ultra high energy region, including the low energy measurement, the recent measurement by OJ and the TA. So I'm Keitaro Fujita from ICRR, University of Tokyo. Yeah, so let's start. So my talk. So firstly, I brief introduce our technique to detect the cosmic ray shower. So we have the surface detector array and the fluorescence detector. So by using the surface detector array to detect observe the air shower particle at the ground, and then we are using the fluorescence detector to observe the shower longitudinal development to detect the fluorescence light. And then also to go down to the low energy measurement, so we are also observing the direct Cherenkov light emitted from the shower by using the fluorescence detector, high elevation fluorescence detector. So this is the Pierre Auger Observatory map, and then they are observing the cosmic ray at Argentina, and then they have the 1,600 surface detector, the water Cherenkov detector, and then the array configuration, this kind of thing, the triangle array configuration, and the detector spacing, the 1.5 kilometer spacing, and the total coverage of the surface detector array is 3,000 square kilometers. And also they have the 4 fluorescence detector site, and here, and here, and here, and here. And in total, the number of telescopes is 24, and the FD is overlooking the surface detector array up to the 30 degree in elevation. So they are constructed the low energy extension around here, and then here is a zoom up this area, and then they are constructing the dense array. The array spacing is 750 meter, and the total coverage is 24 square kilometer. So this red point is infill SD array of OJ detectors. And then they also constructed the high elevation FD because the low energy cosmic rays shower has a higher X mass than the ultra high energy cosmic rays. So then they constructed the 3 high elevation telescope. This is a photo of the heat telescope, and this is a nice view of the observed cosmic ray shower. And this lower field of view is a main OJ FD, and then higher field of view is a heat telescope. So this is a telescope array map. So that they have the 507 scintillation counters, and the array configuration is like a square array configuration. So they each detector spacing the 1.2 kilometer, and the total coverage of the main TASD array is 700 square kilometer. Then they also have the 3 fluorescence detector station at here, here, and here. This is a photo of the fluorescence detectors. And then they have the 38 telescopes in total. And then they also have the low energy extension in the north part of the telescope array at the site. And then this is a map of the low energy extension, so-called tail experiment. So that the target energy is not 10 to the 16 electron volt, 10 to the 15 electron volt, greater than 10 to the 15 electron volt. And the same concept of the TA, main TASD, TA detector are using. So the same, the scintillation counter, deploying like this configuration, and then 10 high elevation fluorescence telescope installed in here. This is a photo of the building or fluorescence detector. And then the blue point is show the field of view of the tail FTs. So then let's move on to the event reconstruction. For the hybrid case, so we perform the time versus angle fit using the FT tube timing, and then surface detector information, because this is a hybrid reconstruction. So then we obtain the shower geometry, and in hybrid case, the most precise shower geometry can obtain. So then using the reconstructed shower axis, that we perform the shower profile reconstruction using the signal intensity obtained by the fluorescence detector. Then we can determine the X marks, and then integration with the shower profile curve, and then we obtain the energy, FD energy. And then we use this technique, and then we achieve the 8% energy resolution in both OJ detector and the TA detector. So for the low energy event case, so we detect the direct Cherenkov light to detect the low energy event, like atmospheric Cherenkov telescope. And then these techniques allow us to achieve the low energy threshold. So then in the reconstruction, so we simultaneously reconstruct for shower geometry and the shower profile, because the direct Cherenkov light is a beaming light. So the shower profile reconstruction can constrain the shower geometry. So then we obtain the shower profile, then integration the shower profile, and obtain the energy. This is the same way as the high energy, the hybrid case. So then these techniques allow us the 1 degree angular resolution and 10% energy resolution at 10 PeV. This resolution is the same in the OJ and the TA case. So let's move on to the ST case. So the surface detector array, the measure the footprint. This is the event map measured by OJ and measured by TA. The size of the circle is proportional to the particle density at the ST position, and then color scale represents the relative timing differences. So using these relative timing differences, we reconstruct the arrival direction. So then we perform the lateral distribution fit to obtain the S1000 in OJ case and the S800 for TA case. So the differences of the shower distance from shower axis is depend on the array configuration and the detector differences. So because the OJ case, the detector separation is detector spacing is 1.5 kilometer, but the TA case is 1.2 kilometers. So then the energy estimated difference in the distance of shower axis. For the OJ case, they take account for the shower attenuation. So because the S1000 for inclined shower is much smaller than the vertical shower case, so then they obtain this kind of attenuation curve obtained by constant intensity cut method, which is the data-driven method, the free from Monte Carlo. So then obtain this kind of the attenuation curve. Then using this curve, they convert to S1000 to S38. So this S38 has a good linear correlation between the FD energies. So this plot is obtained by using the hybrid event, but the all SD event applied this relation, and then obtain the SD energy for OJ case. Now for the TA case, they are using the energy lookup table produced by Monte Carlo. And this energy lookup table as a function of the reconstructed second theta and then reconstructed S800. And the color means the different energies. So then they obtain the energy from the lookup table, then rescaled down to the 27%. Then they obtain the final SD energy. So this is the rescaled SD energy versus the FD energy. So the TA case also the good linear relation like this one. So then let's move on to the energy spectrum measurement. So firstly, I reviewed the new feature in the energy spectrum. So the OJ found the new feature above the ankle, the energy is 13 EeV. So here is the ankle and the new feature of the instep, and then the suppression. And the DA also confirmed that using their data, and then this kind of new spectrum feature. This is a result of using the TAFD spectrum data and the TASD spectrum data. So then this new feature is confirmed in both the northern hemisphere data and the southern hemisphere data. So this table is summarized each spectrum index and then break energy or each point, the ankle and the instep and the cutoff. So let's move on to the comparison of TA OJ spectrum and the TA energy spectrum. So this blue point is the TA ICRC 2019 energy spectrum, and then the black point is the OJ PRD 2020 spectrum data point. You can see the overall agreement, but not perfectly agreement in their energy spectrum. So the energy systematic uncertainty for OJ case is 40%, and the TA case is 21%. So we shift their energy scale within the energy systematic uncertainty. So then shifted spectrum is like this one. So in this plot, the TA energy is scaled down to the 4.5%, and the OJ case, the energy is scaled by plus 4.5%. And then you can see the well agreement of the energy spectrum below around here, but still differences are shown in the highest energy region. So then let's move on to the comparison of the common declination band spectrum. So the TA is located at here, the 39 degree in north, and the OJ is 35 degree in south. So we have the common declination band from minus 15 degrees to plus 24.8 degrees. So using the common declination band spectrum, we compare this plot. And then you can see the well agreement, both measurement, but still we have a bit differences in the highest energy region. So then if we arrow to energy dependent shift 10% per decay, then then their spectrum good agreement in this kind of figure, but we have not, we didn't identify such kind of systematic sources to allow the energy dependent shift. So this is the declination dependencies are shown in here. Here is the OJ spectrum. They divided the 3 declination bands, and you can see that there is no significant declination dependencies in the OJ result. But the TA case, that the different cutoff energy are shown in here. The red point is a lower declination band, which is the same, which is a common declination band of OJ and the TA, but the higher declination band up in this declination band, the energy cutoff energy is differences. So this the briefly summarized for the highest energy region. So in the common declination band, the TA and the OJ spectrum are agreement, but the higher energy, higher declination band only seen by the TAs looks like differences. So then let's move on to the low energy measurement. So firstly, I reviewed the OJ measurement. So this is based on the OJ 750 meter surface detector measurement. So in this measurement, they use energy estimator as S450 meter. The main OJSD is S1000, but in this inferior SD array case, they use the 405 meter. They also using the constant intensity cut method to convert the S415 to 50 to S35, and then this S35 has a good linear correlation with FD energy. So then obtain the SD energy using this relation, and then this is a result of the low energy extension of the OJSD spectrum indicated by red point. Then they are successful to down to the 100 PeV with SD measurement. So this is OJ 750 meter array data and then main OJ SD measurement. Then you can see the smoothly connected both result, and then the low energy measurement also observed angle structure. So this is a heat measurement result. This is a Cherenkov dominated event using to measure the spectrum. So then they are successful down to the 6 PeV with FD measurement. And then you can see the low energy angle structure and the second knee structure. So this is a all energy range of the OJ energy spectrum, the Cherenkov measurement, and then OJ inferior SD array, and the hybrid measurement, and the OJ main SD array result. And this is a combined one. You can see the low energy ankle, second knee, the ankle, the new feature of the instep, and the suppression. You can see. Now for the TA case, so this is a result of the tail FD molecular mode measurement, and this is also the Cherenkov dominated event using to measure the energy spectrum. This is a result of the cosmic energy spectrum, and you can see the knee-like feature, and then low energy ankle, the second knee, and in the case of the tail FD, they can measure the cosmic ray spectrum down to the 2 PeV with FD measurement. This is also using the tail detector, but this measurement is based on the hybrid measurement. So they also measured, observed the secondary structure around the 10 to the 17 electron volt. So this is the all energy range of the energy spectrum. And this is a comparison of the OJ, all energy range of OJ spectrum and the TA spectrum. So you can see the, so how to say, nice agreement, but a little bit differences in the energy scale. This is a summarize of the broken energy point for the OJ case and the TA case. So finally, I present the future prospect for the OJ and the TA. Firstly, the OJ prime. This is a large exposure with the composition sensitivity. So now they are constructing the OJ prime, and they install the scintillaton detector on the water Cherenkov tank, and also they install the radio detector and the small PMT to increase the dynamic range, and also the under muon detector to measure the muon component around here. On the TA case, to focus on the highest energy, which is the energy above the 10 to the 90.5 electron volt. So they installed the new FT in the northern side and the southern side, that in total 12 fluorescence telescope. And then also they construct the new SD array in northern part and the southern part. And they plan to extend the TSD area by factor 4, and then it will be achieved in around 3,000 square kilometer. And the data taking already started, and then they showed the preliminary result of the times for hybrid spectrum and then the times for SD spectrum in the ICRC. So this is a summary of my talk, and then the OJ and the TA are measuring the cosmic ray spectrum, 5 orders of spectrum. And then the OJ and the TA observe the new spectrum feature in instep above the anchor, and then this new feature is confirmed in northern data and the southern data. And then for the comparison of the common declination band, their energy spectrum are well agreement, like this figure. But higher energy region is still differences. So this is a limitation of the statistic or astrophysical sources only in the northern hemisphere. So then we are starting the OJ prime and the times 4, and then also in the future we are trying to understand the low energy comparison, the heat data, the infield data, and the tail FD and the tail SD data. Yeah, that's all my talk.